Right, so what happened? Let's try. You cannot take. When did I lose the screen? Just is it? Okay. So I'm continuing from where I left. So this is the setup that you have, right? A very simplified version. And I want to show you how the current versus voltage graph looks like. So I can check this box, a small graph of this. Can you see the graph? That one small corner, right? Okay, let's see what happens. I will turn on the intensity. I'll leave it at UV so the electrons are definitely coming out. I'll leave it at around 75. Okay, I will zoom in a little bit. So I want to change the okay, I want to change the V first, right? Positive, can you see it's saturated? I'm moving the V to become more and more positive. Electrons become faster and faster, but the rate of arrival of electrons stays the same because the rate of emission of electrons stays the same. This is one of the questions that many of you came out also. Right, one more time. When the V is low, let's say there are 10 electrons coming out per second. When I increase the V, the rate of emission of electrons is still the same, just that the electrons are accelerated, which means the rate of arrival of electrons is the same, which means the current is the same. I do the other way. I will slowly reduce the V and see how fine I can do this. Negative 0.8. Cannot touch. Wow, all cannot touch. So far 0 yet. Okay, negative 0.2. So some will be able to reach and some cannot. Okay, so let me zoom in more on the graph. I'm really limited. I can't change this graph. I try to look for a newer update version. If anyone of you are good with developing these kind of things and are interested to help the community of physics, not just PJC, please let me know. Okay. Right. So what if I change the color? What if I make the frequency higher? Use a higher frequency. So here this applet does something different. It increases the current. So this applet, there's some mistake here. So if I make the current positive and voltage, you can see the current is positive. But just now what was stopping potential? The stopping potential just now was around negative 2. So let's see what this stopping potential is. Oh, yeah, that one was less than negative 2, I guess. Right? So this is still around 2, but a bit more than negative 2, so maybe negative 2.5. I go back to the UV one. The stopping potential is how much? Oh, around 1 point something only. Or 0 point something. So the stopping potential was initially very low. So which matches the graph that we saw. Okay, Ken? Right, so now we go back to the flow. Second is that the second graph of IV that we can get from variation is what happens when you vary the intensity. Now here, when you vary intensity, there are actually two components under intensity. There's frequency of light and there's a rate of arrival of photons. But here we are keeping the frequency constant. So whenever a question asks you, I change the intensity, must yourself, hey, is frequency constant? And this one is also another thing that Cambridge doesn't say, right? So listen carefully and write it down. Usually, 80% of the time, or the general case is when Cambridge say, when I increase intensity, they mean frequency stay the same. Which means stopping potential must stay the same. That's what Cambridge means most of the time. If it's not, they will let you know. Alright? Okay? So you must know how they operate also. I give you the context of how Cambridge operates. I looked at the questions. Right, so once again, most of the time, when they say I change the intensity, I double, I half, they assume frequency constant. If it's not, they will tell you. Okay. So in this case, I've doubled the intensity. I will have doubled the rate of arrival of photons. I will have doubled the rate of emission of electrons, and hence double the current. However, the stopping potential stays the same. Right? Because of the frequency of the photon is the same, the maximum energy of a photon is the same, the work function is the same, the maximum K electron is the same, and hence the stopping potential is the same. Okay? Right. Moving on. Shall we try this? Okay, let's see if we can try this on the applet. Okay. Applet again. IV graph, but now I will be varying intensity. So let me use a graph that's more here. And let me zoom in. Then, if I vary the V, I will get the graph like that. Okay, you can see. Stopping potential, let me maybe make it until it's almost 2. Let me try to make the stopping potential 2. A bit more. Okay, so stopping potential almost 2, right? Or around 2. If I now reduce or half the intensity, what will happen? I reduce the intensity to around 30+%. Check out the IV graph. Can you see? The I is halved. Okay? Can? Now the problem with this is I cannot overlap the two graphs. So you must remember this graph. I move the high intensity. You see that the new IV graph, the saturation current is twice as much. Okay, let's now go back to the lecture. I'm going to rotate around just so that you see. Intensity versus current. This is another variation of graph. It is not the usual IV graph. It's not the stopping potential frequency graph. It is the current versus intensity graph, the II graph. So I will put I intensity, right, to differentiate between the two I's. So if your intensity is higher, your current naturally should be higher. And this current is what? It's the saturation current, obviously. But we are talking about saturation current, not current at any potential. Okay, so let's check it out. Is it true? Applet, turn on this. Let's check out the current versus intensity graph. Right, so let's shift the T to 0. Or close to 0, that doesn't matter. So let's shift the intensity and see what happens. Higher, current goes higher, lower, 0, lower, intensity goes to 0, current is 0. It must pass through the origin. Right, so in your graph, I didn't write down 0. That is actually a critical point. Please write down the 0 as the y-intercept. Okay. If I change the frequency of light, what will happen? Let's say I change to UV and I vary the intensity again. Right? If the rate of photons have changed, the current will also change. So, but once again, it will always be a straight line. Right. The assumption here is always that the frequency is constant, right? Because if intensity is increased through a constant frequency, the rate of arrival of photons. Oh yeah. If we increase the intensity through the increase of frequency, the rate of arrival of photons stays constant. The current will be a horizontal straight line. So this is a variation, right? This is a second variation. So if Cambridge says this, then your current versus intensity graph will actually be a straight line. Very strange. Okay. Right. So I think I've covered the common ones already. Let's look at an example. Example 6. Emitter is illuminated with monochromatic light of wavelength 365, blah, blah, blah. Applied PD there. Find the maximum Ke of the photoelectrons. So you need to know the setup and what the stopping potential means, right? So stopping potential is a proxy to measure the maximum K of photoelectrons. So applying what you have learned in previous lectures, find the stopping potential, read off the graph. Loss in K of electrons, the gain in P is all conversion of energy. EVS is maximum K, half mv squared equals EVS. And here, this is where it appears. I said before, I say again. EVS, note they are italicized. They are physical quantity. This EV behind is a unit for energy. Okay? And so here you just write it down, 1.5 EV. So easy. Okay? Deduce then the work function of the emitter. Oh, how do you do that? You now know the energy of the electron. Remember Einstein's photoelectric effect, there are three components of energy. The light, the metal, and the electron. You have found the electron. Do you know the energy of the light? Well, you don't know yet, but you can find because you know the wavelength of light. Okay? So let's first find the energy of the photon. Right, so E equals to hc over lambda. I leave it to 4SF because it's a subset. Then I rearrange Einstein's photoelectric effect equation. Einstein's equation. So hc over lambda minus Ke max is your work function. Then you get the energy from the work function. 1.91 eV. Then part C, draw a new IV graph for experiment which uses twice the intensity of light but the same wavelength. So if same wavelength, stopping potential must be the same. And same frequency means the energy of photon must be the same. When you increase intensity, you are then only increasing the rate of arrival of photons. So using that argument, you get this one. Okay? Right. So I'm going to give you some time to discuss example 6 or anything you don't know. And if you already know, I'm going to give you 8 minutes to try example 7. Okay, can you do that? Okay, right. Very encouraged that a number of you are trying seriously. Very good. Uh, some didn't. I encourage you to try, right? Right. Because the common feedback that we get from students is that, oh, the lecture, example, so easy. Then tutorial suddenly why so hard? Actually, uh, for my lectures, I try to put it about the same, right? About the same, but tutorial still slightly harder. Okay? Have to be lah, huh? Because it is not lecture notes alone, right? The whole pedagogy is that I must start you off easy, and then ease you into the harder ones. The tutorial is an integral part of learning, right? To practice and try. So I start you example 7, which is one of the easier ones, right? Those of you who tried, good for you. So, which metal requires a higher frequency of light to produce photons?
Since the minimum photon energy HF not right needed to release electrons from metal must equal the work function of the metal. Hence, the higher the work function, the higher the frequency. Okay, so aluminum is actually higher than that of. Right, so this will roughly be a 2-mark question that will start you off in the exams of text. Right? Pretty simple. Does it ease you off? B, calculate the minimum frequency that will produce photoelectrons from each surface. Again, the same equation. So work function equals to HF naught. For aluminum, just plug it in. For calcium, plug it in. Okay. I'll give you some time to copy this. Yes, sure. And how many of you got this answer? Very good. Now I see a good 30-40%. Right. Knowing this, you are already 2/3 of photoelectric effect equation. You already 2/3 of it, because you must know E equals HF, energy of photon. You must know work function. So that's already 2/3 of the equation. You already. The last part is the EDS part. Very good. Okay, almost finished. A few more. Okay, so we wait for one more. Try to finish. Right. Part C. Does calcium exhibit photoelectric effect for red light of that wavelength? Right off the bat, I think answer should be no. But let's see. So the energy of that wavelength using E equals HF and then HC over lambda, you get this amount. Is this higher or lower than calcium? It is lower than the work function, so no. Okay? No. And here I want you to have this sensitivity. I think the only metals that you can use normal light and have photoelectric effect is cesium and sodium, the very reactive metal. So most of the other metals, right, no, you usually need UV. Right? So generally the range of light of EM should be UV. And so even before answering, you know the answer.
Instead of comparing the energy of the photon, they compare the frequency.
Can. So if you found the frequency for this wavelength, you'll find that this frequency is lower than the threshold frequency, then it should not emit. That's fine. Alright. So I selected reasonable questions for your tutorial, many from past year papers. It gets harder towards the end, obviously. Right, it starts off with the component part, but gets harder towards the end. Right, so it should be interesting for you to consolidate your learning. Right? So, summary. I've given you the definitions for all this, and you must remember all this. Right? I'm sure your tutors have been stressing to you as I have been to my classes. We looked at the past year A-level paper, 30% is definitions. So out of 10 marks, 3 is definitions. You better go and remember it. Now I say again, I know word on the street is that I learn physics because I don't want to memorize, right? Because that's how you all got influenced to take physics, right? That you're choosing your subject only. Because you'll say, oh, bio need a lot of memorization. But not true. Doesn't mean that a subject that requires a lot of thinking doesn't need memorization. Not true, So you need to memorize to know the concepts, then you can think using those concepts, Wow. So when you tell your juniors, you must tell them, if you like to memorize things and think very deeply about those things, then you come and study physics. Okay? Get the word correct. Don't categorize physics as the subject that don't need to memorize. It's completely wrong. Okay? Next. This one is the most important, right? Let me recap. Photoelectric effect is essentially about conservation of energy. And Einstein's photoelectric effect is about a particular. Particular? Is that your typical word? Particular? I don't know, man. Okay, so it's about a specific electron, the most energetic one. Okay, so do not confuse the general conservation of energy with Einstein's photoelectric effect. And it's given like this, right? And I've given you how they can morph the equation. Obviously, there's also Hc over lambda and Hc over lambda naught. But I've given you the general possibilities. They are the same, equivalent, right? Equation. Next, I also given you the explanation part. I've looked at the past year papers. 3 marks for definition, 3 to 4 marks for explanation. Explain why. Threshold frequency suggests that light is particulate in nature. Explain why. Instantaneous emission suggests that it's particulate in nature. Explain why the maximum K depending on frequency and not intensity, explains that light is particular in nature. So these are the questions that you can ask you. And I've given you all the explanation there. Don't say don't have. It's there now. I even nicely categorized all the box for you. Okay? So it's there. And it came out. Okay? So in a quantum question out of 10, generally 3 marks definition, 3 to 4 marks explanation, and the rest calculation. Okay? Because the equation, if you look at it, there's only one equation. I took 3 lectures to explain to you one equation. You better know it. Okay, and lastly, actually, why you want to study quantum? It's so small, it doesn't affect us. It's because of this. It's a mind-blowing revolution, right? Because if light is both a wave and a particle, then you question yourself that a particle can it be a wave? When you know more things, you have more questions. Agree? The same thing in this physics. At that moment in time, the scientists were, oh my god, can an electron have wave properties? Right? Can a basketball have a wave property? Because if they have, which means that they can interfere with each other, no? Because wave can interfere and superposition with each other. And in the later chapter, the next lecture, quantum 2, you'll see that electrons do exhibit wave properties and they do interfere with each other, which is very, very surprising to the scientists of those times. And once you know this, right, and how science progresses, just one last word on this before I let you go, is this. Science has always been like that. You must first be able to observe, then you understand, then the next stage is the manipulation. We have observed how engines or how energy works, then we make measurements, then we can manipulate to create steam engines. We have seen how electromagnetism works. We observe, we measure, then we create things that create your handphones. So what is next for quantum? Quantum computer, possible, right? The one computer that can break all the usual codes. Then you need a quantum computer to prevent the breakage of those codes. A quantum system. Right? So quantum can become the shield, your cyber defense, and also your cyber sword to break through all those shields. Right? So there's a race for this, a quantum computer. There's a race for this. I'm not sure who is winning. Right? So that's it. Thank you very much. Enjoy quantum lecture 2. Oh wait, feedback. In AC lecture, I didn't ask for this, so snapshot please. I only had like a paltry 36 responses, so give me a feedback, let me know what you like, what you don't like. Then I can know what to do for future, alright? Thank you, and have a nice day, bye-bye. If you have questions, come in. Hey, what's the issue?